All right, this is our last video dealing with thermodynamics. I know you're excited about that. One of the things as I'm looking at these equations here on the screen, one of the things to remember is that with one of the things we learned about in this unit is called Hess's law. And Hess's law, remember, means you can add, you can double, you can flip, you can do those to different equations to get a new enthalpy change for a different reaction. Okay, you can use entropy, delta S. You can use Hess's law with delta S as well, and you can also use it with delta G's. Again, just like with enthalpy, you can flip equations, double equations, cut them in half, add them together to get a new enthalpy change, a new entropy change, or a new delta G value for a reaction. So Hess's law applies not only to enthalpy, but it also applies to entropy and Gibbs free energy as well. Okay, and just like the earlier problems we saw where you can find the enthalpy change for a reaction using the enthalpy of formation of the products minus the enthalpy of formation of the reactants. And then delta S, you can find the same thing. The entropy change for the reaction is the absolute entropy of the products minus the absolute entropy of the reactants. And now we have our third equation that looks exactly like the other two, is you can find the Gibbs free energy, or the delta G value, by using the entropy, or it's not the entropy, the Gibbs free energy of formation of the products, and the Gibbs free energy of formation of the reactants. So since it's of formation, just like enthalpies of formation, that when something's in its elemental form, it does have a Gibbs free energy of 0. Okay, remember that entropy is the only one that even when it's in its elemental form, it still has some entropy. It still has some disorder associated with it unless it's at 0 Kelvin. Okay, but delta H of formation and delta G's of formation have enthalpies and Gibbs free energies of 0 when they are in their elemental form. So just like this equation here, you take the products, you add them all up, you take the reactants, you add them all up, and then you subtract them. Products minus reactants. And then once again, if delta G is positive, then the reaction is not thermodynamically favorable. If delta G is negative, then it is thermodynamically favorable. And then again, if it's 0, then the reaction is not favored in either direction. I believe we talked about in the last video. And therefore, you have reached equilibrium. Okay, and equilibrium is going to be our next unit. Okay, so I just want to introduce this equation right now. You won't see anything on it on the most recent test, but in the equilibrium one you might. Okay, I just want to understand here that when delta G, if this value is negative, and you've got that negative sign right there, R is always positive, temperature is always positive. Okay, and natural log, the way that natural log works, the natural log of a number that's greater than 1 is positive. And the natural log of a number that's less than 1 is negative. Okay? And so what this tells you is that when the equilibrium constant is greater than 1, then delta G is going to be negative. So if K is greater than 1, then delta G is negative. If K is less than 1, then delta G is positive. So what does that tell you? It tells you that when it's thermodynamically favorable, the equilibrium constant is greater than 1. And again, what does that mean? Don't worry about what equilibrium constant means yet. Okay? When delta G is positive, that means that the equilibrium constant is less than 1. Okay? And that's really all you need to know about that. Okay? And then really our final thing here is understanding that, and again, this equation is not given on the AP equation sheet, so certainly they're not going to ask about it. But notice that there's a delta G standard, and there's a delta G without the little degree sign up in the corner, which means it's under non-standard conditions. Okay, when that happens, okay, it means that the temperature or the pressure isn't the right temperature or the right pressure, or the concentration isn't 1 mole or something like that. Okay, and all you really need to understand is that sometimes if that happens, when you're outside of standard conditions, sometimes if a reaction is thermodynamically favorable, you might not get very many products. Like if the temperature is really low, you might not get very many products simply because there's so little energy in there because the temperature is so low. Okay, and sometimes, again, a non-favored reaction, sometimes delta G is positive, you might actually get some products. And again, simply because sometimes those concentrations and pressures are not at the standard conditions. Again, don't worry really about that. This equation is going to come up in a different form later on in Unit 7. And I think that's what I talk about here in Unit 7, where we're going to talk about how that affects electrochemistry. Okay, and then our final thing here is about catalysts. So we learned in Unit 4, so from Unit 4, we learned that catalysts obviously are one of the 4 things that determine how fast or slow a reaction goes. And we know the job of a catalyst is to make the reaction go faster, and it does that by producing an alternative reaction mechanism where the slow step has a lower activation energy. Okay, so it will cause the reaction to proceed faster, but a catalyst does not affect the thermodynamic favorability of a reaction. Okay, which means you make a reaction go faster, that's great, but that does not make it more thermodynamically favorable or less thermodynamically favorable. Catalysts have no effect on the value of delta G. They simply cause the rate of the reaction to increase.